Emostel.
Hello, you're welcome to this video. In this video, we are going to be determining the size of an error. We want to just see how the size of an error can be determined when you take the same measurement several times. Okay, so it's just like an extension of random error. Okay, we want to just talk about how random errors can be handled in the lab, how we can handle it using statistics and all that, you get. So random error, especially the one coming from observational error, okay? So how observational random error can be corrected using statistics is what this topic is really centered about, so that we can be able to have some form of range of approximate values that we can work with or that we can relate with, okay? So now, this thing that you are seeing behind me here is a result obtained from a repeated measurement of something. Okay, it's an example from the course material board. Just a repeated measurement, let's say a repeated measurement of the time taken for a number of oscillations. So let's say the first time the person measured it was 3.69. The next measurement was 3.67. The person tried it again, 3.68. The person tried it again, 3.69. And again, and again, and again, and again, until it produced all this. The average of the measurements, obviously, is 3.68. That is, we took the average from this plus 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 this, divided by the number of times the measurement was taken. So the number of time is what this represents, which means 8 times. So when you add up everything divided by 8, you get this average value. And that is what produced this. All right, but that is not really enough. Okay, we have been able to find the average value, right? So, but we want to know the deviation. Deviation means that we want to see the distance between each of the measurements, the difference between each of the measurements from the average value. Okay? All right, so we know that, okay, the average measurement is 3.68. So we want to see how each of these values deviate from that 3.68. And so what we are going to do to find the deviation, we'll subtract each of the value from the average measurement. So I need to save time. Well, 3.69 minus 3.68 is going to give us 0.01, right? 3.67 minus 3.68 is going to give us minus 0.01. All right, so 3.68 minus 3.68 is 0.00. All right, 3.69 minus 3.68 is 0.01. All right, so 3.68 minus 3.68, 0.00. 3.69 minus 3.68, 0.01. And then 3.66 minus 3.68 is negative 0.02. And then 3.67 minus 3.68, okay, we have minus 0.01. Okay? All right, so having all of this, so we are just going to focus on the positive, value. Let's say we take the absolute value. The reason is that we only care about the distance between the actual value read in each case and the average value. So I think we are just keen about that distance, right? Not about the negative or positive. So at the end of the day, we just focus only on the positive value, or because even we might not even really care, because it will still be rooted. Okay? All right, so what we do here now, in this case, after all of this, we are going to find the square in each case. Okay, so let's calculate, let's just find it. We want to find the mean, or before we do that, please, hold on. We may not necessarily need that square, okay? We'll just calculate the we add up everything, we take the absolute value, we add up everything and you find the mean of the deviation. So that will give us the mean deviation. So taking the absolute value now, what are we going to have? Absolute value means the positive result of each case, okay? So let's let me take this one as D. I would rather represent it as this, absolute value D. So if we do it as absolute value D, okay, we are going to have only the positive results. Whether it is supposed to be minus or not, we'll keep only the positive results for absolute value of D, right? Absolute value is just the distance between two values, okay? We don't care whether it is negative or positive, okay? Now, the next thing you do is to find the average of this. So the average of the absolute value will be given as bar D. The average of the absolute value will be given as bar D. So the average of the absolute value is like, okay, we add up everything here. This plus this plus this plus this. I don't think I need the calculator for that. So 1 plus 1, 2, 3, 4, 5, 6, 7. Bar D will be equal to the total value, all right? Let me take this one as the summation of this. So let's find the summation first. We have 1, 2, 3, 4, 5, 6, 7. We have 7, 0, 0, 0, 0, 0, 0, okay, 0. Then everything is 0. So we have 0.07. That's the summation of everything here. So bar D is going to be summation of what? The absolute value D divided by n, which means where n is the number of times the experiment is performed. So we are trying to find the mean of the deviation. That's what we are finding. So the mean of the deviation is going to be, or the average of the deviation. These are the deviation, okay? Deviation is just the distance between each value and the average value, okay? So the difference between each value and average value is deviation. So the total deviation, the total of everything is 0.07. So the mean deviation will be this over n. So then we have bar D is not equal to this 0.07. You're not finding the square, there's no need for this analysis that we are doing. So we have 0.07 divided by n. So we have bar D equal to, okay, n is 8, so 0.07 divided by 8. So now I think I'm going to need this. Okay, so we have 0.07 divided by 8. Okay, so the answer we got for that is 0.00875. Okay, but remember that we are going to round off our answer to have as many significant digits as the one of the least precise elements. And then this one now is only 1. Okay, even in both cases it's 1. The significant digit in both cases is 1. So we are going to let our answer to have only one significant digit. And so that is going to be 0.009. So we stop at 00 point. That is the result for bar D, 0.009. Okay, now there is something that we call precision index. The formula for precision index, as given in the material, okay, the formula for precision index is equal to the square root, okay, of D divided by n. Okay, so that is bar D over, okay, sorry, bar D, the mean deviation divided by the square root of n. I beg your pardon, sorry. So it's going to be, this is what we call precision index. Precision index is just like a measurement that is trying to tell us how precise these all readings are. Okay, it's just a measurement of the precision or the closeness of the values of the measurements that you had in that series of experiments. Okay, so precision index is going to be bar d over root n according to the formula for finding this. So bar d over root n is going to be like, okay, 0.009 divided by the square root of 8, because n is equal to 8. The experiment was done 8 times. So again, we're going to calculate, okay, 0.009 divided by the square root of 8. Let me change it to scientific. Divided by the square root of 8. Okay, so the answer here is, so the precision index, let's represent it with letter Z. The precision index is equal to, or S, I think in the course it was S that was used. Okay, so we have 0.003. Okay, so the precision index S is 0.003, and that is the answer. So with this now we have been able to determine the size of the error. Okay, the size of the error in this measurement, okay, is given as 0.003. So therefore, we will say that the actual, we will not say actual value, we say actual value. Please, before we can even determine the actual value, there is a factor that we must consider. The factor to be considered is that the precision index, we check it, is the precision index greater or lesser than the maximum possible error, right? If you look at it very well, this is the average value. The average value is actually 3.68. Ideally, we are supposed to say that the actual value or the approximate value is going to be equal to the average value plus or minus the precision index. Okay, so which means I'm supposed to write my answer as the average value, which is 3.68. That is the average of the 8 measurements, 3.68 plus or minus the precision index, which I just got, 0.003. So this is how I'm supposed to write my answer normally. Okay, this is how I'm, so which means that, okay, the measurements that we took, all right, is equal to 3.68. Then the error part of it, the error part of it, like with the range of error that we could have in the measurement, okay, due to precision issue, okay, due to the maybe the value falls in between two minimum values and all of that, is what? 0.003. Okay, so that is what this this precision index represents. Okay, this value, it just tells us the size of the value of the error, okay, that we have in taking the actual measurement. So we are going to say, okay, the average measurement plus or minus this error value, okay? But then we need to, before we can say this is our final answer, we need to check if the precision index that we derive, if it is up to the maximum possible error. The maximum possible error actually is 0.005, okay? Because if we look at it very well, the unit of measure is 0.01. That's the unit of measure. So if you divide the unit of measure by 2, you get the possible error, which is 0.005. So the possible error is actually 0.005. Meanwhile, the precision index is what? 0.003. So we see that the precision index is not up to the possible error. So if you want to write the maximum possible error, so if you want to present our answer, just because of this reason, just because 0.003, which is the precision index, is not up to the maximum possible error, just because of that, we are going to ignore it. So our final answer is going to be 3.68, okay, plus or minus 0.005, meaning that we are going to stick to the maximum possible error. But assuming the precision index we got is greater than the maximum possible error, then we are going to consider it in our answer. So the final results, or the final results of the final answer depends on whether or not the final value that you are going to write depends on whether or not the result you got for the precision index is greater than the maximum possible error or less. But left to me anyway, okay, this answer would have been more preferred. Okay, like if you want to just look at it ideally, after the precision index, because if you get a value like the precision index is something like, let's say 0.006 or 0.007, that's the precision index, okay? Okay, I would have preferred that, okay, the maximum possible error should be able to, that is when I will say, okay, I want to use the maximum possible error, because it gives us, but the reason why I see that we choose the one with the highest value, which in this case is the maximum possible error, the reason why it is chosen is just to give enough space or enough gap for the possibility of error. So we look at the one that is bigger among the two. So since the precision index is less than the maximum possible error, we will stick to the maximum possible error. But if the precision index is greater than the maximum possible error, we stick to the precision index. So we are just doing this just for us to be able to have a wider range of possibility of error so that we can be able to compensate for any error within that range. So that is the reason why it is like that. All right, so hope you get it now. All right, in that case, we believe that you've understood how to find the size of an error. In the next video, we are going to be doing some sort of error propagation. See you in that video. Bye.